Okay, in this lecture we're going to talk about graphing general polynomials. We're going to start with the simpler ones, and that is, let's suppose f of x equals ax to the power of n. So remember, the n is the degree of the polynomial. And so far we've talked about, say, y equals x squared. And then, of course, we looked at, that was our basic function. Then we looked at, well, what would f of x equals 2x squared look like? What would, say, g of x equals a half x squared look like? And say, what would negative 2x squared look like? All right, well, let's move it up a notch from an x squared to a cube. So let's suppose we start with our basic function as y equals x cubed. And we'll do a rough sketch here. And so we know that our x cubed looks like this. Around about a bit around further than that. All right, and so it looks like this. All right, well, what would, of course, f of x equal 2x cubed look like? Well, of course, that stretches it vertically, you know that, so it's going to come in closer here and stay closer here. And that would be this one. Stretches it vertically. Okay, so what about a half? Well, of course, that shrinks it vertically, so that would be moving it out a bit further, like so. Right, and that, of course, would be, let's call that g of x equals a half x cubed. All right, well, what if we have now h of x is equal to negative 2x cubed? Right, well, that, of course, will invert, all right, this inside one. So in actual fact, we'd end up with like so. All right, and so you can see all the same translations still actually remain the same, okay? Now, what happens if we now want to look at say, a general polynomial function? And, of course, a general polynomial function will, first of all, have this form. All right, again, where n is the degree. And we now want to look at degrees greater than 2 and perhaps 3, which is what we just looked at here. And what does this a do? Well, if we look at the size of a, if it is, of course, greater than 1, then we do get a vertical stretch. Okay? Right, now if the size of a is less than 1 but greater than 0, then of course we get a vertical shrinking, all right, like so. Now, of course, if what if we have a f of x is equal to negative a of x to the n? Okay, well, we get a reflection across the x-axis. Right, just as we did before. So if I look at all kinds of translations of this, for example, if I have f of x equals ax to the n plus k, that will move it up or down k units, depending on whether k is positive or negative. Right, it'll be up when k is positive, and it'll be down when k is negative. Okay. All right, what if we have something like f of x equals a by x minus, say, h to the n? Then we're going to have a horizontal, all right, shift or translation. And of course, it's going to be when h is greater than 0. All right, it's going to be to the right. All right, h units. If h is less than 0, then it's going to be to the left. All right, so we still have these particular things. And of course, when we have all of these put together, right, then we apply all of those particular transformations. All right, so let's have a look at some examples of this. All right, so example 1. Let's suppose I want to graph f of x equals x cubed minus 2. Right, well we know that our x cubed, it looks like this, minus 2 means we bring it down 2 units. And it looks like this. Okay. All right, so here's our x cubed. And this is going to be our x cubed minus 2, where we go down 2 units. We drop all of it down 2 units. Okay, what if we have, so let's look at example 2. Okay, what if I have x minus 3 to the power of 5? Let's call it g of x. Right, so we start with our power of 5, which is really just a very narrow here, but then flattens out a lot here, like so. Alright, so this is y equals x to the power of 5. Alright, now what happens if we do negative 3? Well, of course, this will mean it will go to the right 3. Alright, and so we have exactly the same thing. It's sort of narrow in here, flattens out across here, and up we go, where this is negative 3. Alright, what about if we have a combination of these kinds of things, and let's suppose we have something like negative a half by x plus 2 to the power of 4, say minus 3. Alright, now if we have this particular situation, a bit wobbly there, but let's have a look. Now it's a power of 4. Now power of 4 actually is fairly narrow here. Flattens down because numbers less than 1 really get small. And up we come, like so. Alright, so now what happens if we now do a negative a half? Well, of course it flattens out, but it goes out wider. Like so. When we add 2, that means we'll go this way 2, so it's going to be moved 2 units this way. And then finally it's going to be negative 3, so we've got to go down 3. And so we end up with this kind of thing. And there it is. Okay. Alright, so that's example 3. Okay, so you can see how the translations are all still working quite well. I now want to talk a little bit about what happens if we have a even degreed polynomial. Okay, so if I have an even degree polynomial, right, this means that when we have this means that the highest exponent is even. So let's suppose it's a squared, it's a power of 4, power of 6, power of 8, and so forth. Now, if we have something like that, then this can often be the scenario. So it could come, turn here, come down, alright, turn, and then just turn back up, like so. Right, now you notice here that we have, this is degree 4, and we have 1, 2 real root or zeros. Okay. Alright, now also I want you to notice here is that I have 1, 2, 3 turns. Interestingly enough, if I now look at a power of degree 6 polynomial, I could have something like this. And notice that we have, so this is degree 6. And we have 1, 2, 3, 4 zeros. And that's real zeros. Right, now of course, in both of these cases, we do have a turn here and here, so we do have complex zeros. And remember that we can have up to 4 complex zeros, and remember all real zeros are complex zeros according to the fundamental theorem of algebra. Here, of course, we have 1, 2, 3, 4, 5 turns. Okay, so we have 5 turns. Okay, and so consequently we have 1, 2, 3, 4 real zeros, so there's 2 non-real, which are 2 complex, which are not real. The real ones are complex, but we can have 2 complex ones which are not real. And so we have that particular scenario for degree 6. If I had degree 8, I could do it again. And of course, we would have 7 turns. And you can see that the number of turns follows by 1 less than the degree. It's equal to n minus 1. 1 less than the degree. Right, the next thing I want to talk about is what about an odd degreed polynomial? Right, so in other words, what we're talking about here is the highest exponent is odd. Say it's power of 1, power of 3, power of 5, power of 7, and so forth. Right, now we have a couple of scenarios that can happen here. Let's suppose we have degree 3, then we would end up with something that looks like this. Notice that we could have 3 real zeros. And of course, real zeros are complex, so we have 3 complex. We can't have any more than 3 according to the fundamental theorem of algebra. Notice that we have 1, 2 turns. So it follows the same pattern. Number of turns is 1 less than the degree. All right, what if we have, we could have a degree 3 where we only have 1. So it could turn like this and then come down. So we have 1 0, 1 real zero. Okay, and we still have 2 turns though. Okay, and of course if we have degree 5, then we're just going to add a turn in here. So let's have a look at a degree 5. Okay, so we could go up here, turn, up here, turn, come back down and turn here. So notice that we have 1, 2, 3 real zeros. We still have 1, 2, 3, 4 turns. Right, we have 1, 2, 3, 5 complex zeros, 3 of which are real. Okay, and so you can see here how this actually follows a pattern according to whether we have an odd degreed polynomial or a even degreed polynomial. But at the end of the day, we see that it happens in both cases that the number of turns will be equal to 1 less, okay, all right, than the 1 less than the actual degree. And that is at least, all right, and I should point this out, that there are at most, all right, so we can't have any more than n minus 1. Okay, we may have less, and a good example of that is a degree, the cube polynomial, which is like this. Okay, and there it is. So it actually has really got 1 turn like so. Okay. Alright, so it has at most 3, 2 it should be. Alright, notice it should have at most 2 being a cubic, but of course we could have 1. Okay, but remember it's at most 2. Alright, so that's a brief introduction there to remember graphing general polynomials, okay, of n degree, and of course our transformations still all work the same. And now of course we're talking about odd degree polynomials and even degree polynomials, and the next lecture we're going to talk about how the odd and even of the degree will affect the end behavior, what's called the end behavior of the polynomial.